Afternoon, my name is Ralph Brooker. I'm with SatProf. We developed the training program for GVF, and I want to tell you about how we use the training program to help prevent interference from happening, in particular from VSATs. There are several key reasons that interference happens, especially unintentional interference from VSAT installers. The most endemic and difficult one to deal with is adjacent satellite interference, where satellite terminal installers don't quite point the antenna accurately enough, and because the small antennas have a wide beam width, even a small mispointing will cause a adjacent satellite effect. So you can see here this beam is only moving a few tenths of a degree, but the side lobes are already encroaching on the neighbors. So if I can click over to the next view, you can see it from the side. If you look down from the top, you can see that these satellites are only 2 degrees apart. The beam width of a typical small VSAT antenna will be 1 meter, 75 centimeters of KU band. That's about how wide it is. So it just barely fits between the satellites. So what we do in the GVF training program is to teach the installers to not just peak the signal, which is not a very accurate way to do it, but to actually center it between the neighbors. And you can see here on this little diagram a more illustrative example. If you have a small antenna, by physics, small antennas always have wide beams. It doesn't matter what kind of antenna, if it's a flat panel, parabolic, anything. If it's a multi-wavelength antenna, if it's smaller, it's got a wider beam. So, and the pressure is always on to have the minimum possible beam width, or the minimum possible antenna size for economic reasons. So that means that necessarily antennas go small enough so that the interference is just about acceptable. But it's always assumed that antennas are pointed perfectly. Whereas if you have large antennas, even if you mispoint a little bit, it's going to be apparent to the installer when they're peaking it that they're not peaked right, long before they start to make interference. So that's why it's so important with the training program when you're trying to reach low-level technicians. They're usually installing small antennas. It's more important to train them than it is people working on big expensive stations. Okay, this whole simulator lets you see the effective beam width, effective antenna size on beam width. So here I can drag this antenna diameter up and down, and you're seeing here the beam width both in transmit and receive. This particular animation is called squint because we also use it to teach about the difference in beam direction from transmit to receive for circular pole. But you can use this just as well to see the effect of small antennas. So as you go a little bit off from the side, as you mispoint just a few degrees, you can see how the beam rapidly comes up to the adjacent satellite over here. So I'll go back to like a 74 centimeter KU band. That's how wide it really is. And you can see that just a few tenths of a dB of pointing error up there translates into a big effect over here. So that's why in our training course we teach in the center of the beam. We make you turn the antenna way down the side, then turn it back to the other side, count how many turns of the adjuster took, and then go back to the middle. That's what we call the beam balance method. And we simulate that and we make you demonstrate it, and you can't pass the course and get certified unless you can do that correctly. When you measure signal strength with any kind of meter, modem, spectrum analyzer, there's always random fluctuations in your readings, several tenths of a dB, sometimes half a dB. But if you measure off to the side, the same fluctuation in level translates into a much smaller angular precision. So by measuring down at these two side points, we get very fine angular precision. But we have to teach that to the humans to do that with wrenches and nuts and bolts. And this is the theory we take them through. And these animations are all from the 510 course. Let's skip through to the next. Cross-pole, probably the number 2 most problematic issue for interference, especially KU band. The installer is expected to align this ultimately within about 1 degree or 2 degrees of rotation. And there's no fine precision indication on there. So the way they have to do it is to adjust it back and forth. So we teach that in several different ways, but one is we teach them to pre-calculate it and use a little level that can get you within about 2 or 3 degrees. That's pretty close. And we walk them through the procedure for doing that. And then for a fine adjustment, you have to really call and get feedback from the other end of the link. So usually that's done with calling the satellite operator. They find your carrier and read it back to you. So this is what happens if you don't have polarization set quite right when you're transmitting your carrier. This is the channel you're supposed to be on, transponder you're supposed to be on. This is the transponder on the other polarization. This yellow signal here is somebody else's signal. So the red one is it's the same signal, but it shows up in the cross-pole transponder. And unless you get it very well suppressed by adjusting the angle of this feed, I'm just moving in tiny increments. You can see it makes a really big difference as to how much interference ratio there is between what's desired and what's interference. So getting that within about 1 or 2 degrees of rotation that's the name of the game. And finally, the third major cause of interference is bad connectors. It's retransmission of local ambient signals, often from cellular signals, mobile phones. GSM signals will get into a certain part of the IF band, travel up the cable, go to the buck, and the antenna get up, converted, amplified, and they show up as little interference signals on the transponders. In some cases, satellite operators can even take a cell phone and receive it. And that's how they figure out. Sometimes they've actually tracked it down by catching the ID signals off the GSM with a phone or a hub base station. So it's really important when you're training technicians that they know the right way to correctly terminate cables, because most of those issues are the grounding is not properly connected to the shielding, and the connector, if it just is connected through the center, acts as an antenna, and it's a very efficient monopole antenna. So we have lots of animations for that, and we teach them the principles of it, and later on we have a decision-making simulator that makes them walk through the correct processes for preparing, say, quad shield RG6 cable. And finally, for manually operated stations like S&G trucks or Earth stations, there's been for a number of years an ITU sanctioned document called the Universal Access Procedure. This was tweaked about 4 or 5 years ago by our RFI-EUI committee, and they changed it into the General Access Procedure. And it's basically good manners, best practices for bringing up carriers, come up with the right frequency, the right modulation, the right bandwidth, the right power in those orders. So we teach that as part of our 532 course, which is oriented towards manually uplinked carriers. And this is a sample slide from that. So that's in a nutshell, that's how we teach interference prevention in the GVF program. Yeah, thank you.